Hello everyone, how are you? This is Jun, your lecturer for Econ Statistics. Today we're gonna talk about slide 4, which is measures of variability. In chapter 3, we learned what measurable locations. So when we deal with data, um, we want to describe what is the average or how the data is distributed, right? So in previous slide, we were talking about what is their mean and what is their median, etc. Now in this chapter, we're gonna talk about, okay, what is the variance and what is the standard deviation and how much variation the data has. So let me give you some examples. So those are relevant topics are in chapter 4.2 and 4.3. We're gonna learn range and interquartile range and variance and standard deviation. These are very important concepts because when we talk about data, mean and variance are pretty much most important two variables we want to discuss. So later part, when you guys discuss the Tom project, which I will describe later, sometime in October or something like that, you might want to discuss, okay, what is the variability of your data sets and what is the standard deviation and what is the mean, etc., etc. I will give you more examples later. Let's talk about two distribution, one in blue and the other is in red. And based on two distributions, which has the greater mean? So we might want to pause this video and think about it. So I'm asking which one has greater mean. The answer would be what? Of course, the red one, because that is more toward to the right. So it has higher mean because mean is somewhere around here, but the mean for red is actually somewhere here, but mean for blue is somewhere here. So it's gonna be higher. So the next question is, okay, what is the mean in this case? So again, you might want to pause this video. And the answer for this question is, okay, the mean for blue is somewhere around here. And the mean for this red one is also somewhere around here. So you cannot tell which one has higher mean or lower mean. So answer is E. Okay, so when we talk about the data sets, we talk about measurable locations. So it captures where the observations are centered around. So for example, if we talk about this red one, okay, their mean is around here, and we can talk about, okay, based on this center, these distributions are something like that. So those are some information we can take from here. Okay, we can also talk about measurable dispersions. So variability or speed capture how concentrated or dispersed observations are. Open measures of location do not provide enough information. For example, this one, the red and blue one, both have about similar average, but it doesn't tell us about, okay, how the data is distributed, right? So based on these two distribution, which one is more widely distributed, do you think? Think about it. Okay, I will come back this issue. Okay. So it doesn't give you enough information. For example, this blue one is more widely distributed. As you can see, it has a lot of range, from this one to this, and much more variability around this blue one. On the other hand, more data are near mean and less variation for mean. This red one. So despite their means are about similar, this blue one has higher variances or variability, say, more spread it out, data is more spread it out. So we want to capture this information in this chapter. So two examples. In terms of annual average temperature, where is warmer? So if we take a look at this data, okay, Honolulu is about 77 Fahrenheit and Phoenix is about 75. I mean, their average are about the same. But information we want to discuss is, okay, the range for the weather is like much higher, 45.6 to 106 in Phoenix. On the other hand, the variations or the range are very small in Honolulu, despite their temperatures are the same. So comparing to the previous cases, the Honolulu would look like something like that, but Phoenix would be something like that in comparing to the previous cases. So Phoenix is more like a blue, and Honolulu is more like a red in previous distributions. Often we are interested in how much a random variable can vary. So these are some examples, like dispersion of income, inequality, or risk, or lack of reliabilities. Those are some economics to think about. So we will learn two types of measures of dispersion. One is a range and interquartile range, and the other is a variance. I mean, there are trade-offs between that, so I will go from range first and move to the variances. So the random variable varies between maximum and minimum. For example, the range, this is how you calculate a maximum minus minimum. So the greater the range is, the more dispersed the random variable is. So Honolulu, the range is 21.6. For Phoenix is like a 50.5. So in terms of range, Phoenix has much higher range. So advantage is what? Very simple and intuitive, very easy to calculate. Disadvantage is very sensitive to outlier. For example, in one day in Phoenix, if the highest temperature would be 120, for example, instead of 106, then your range would increase dramatically due to just one day higher temperature. Similarly, that happened for Honolulu as well. So it's very sensitive to the outlier. That is a disadvantage. Another way of talking about the dispersion of data is interquartile range. So that 25 percentile is first quartiles, and 75 is third quartile, and 50 is second quartile, or this is a median. It's basically the same concept. So interquartile range is third quartile minus first quartile. The subtraction between this would give you, okay, what would be the range? So this is how you get the interquartile range formula. It is a range for the middle 50% of observation. So to overcome this disadvantage, we are looking at middle 50% of observation. So it's much more, it's less sensitive to outliers than the range, And the other concept is deviations. Basically, we are interested in how far the data are from the center. So if this is a notation for mean and mu, mean and average. So X bar, we use this for population average. And mu, actually X bar is a sample average, and mu is a population average. Sorry for the confusion. And the distance of an observation xi from the center is xi minus x bar. So comparing to the sample mean, for example, your SAT score was 1500, but average was 1450. Then the distance from the observation, your SAT score from the mean would be 50. So in other words, it's 1500 minus 1450, which was the average. So it is called the deviation of xi. So comparing to the average value x bar, what would be your deviations? It can be applied to many other things. For example, the average, average high school GPA was like a 3.4, say. Then your GPA was 3.6. Then your deviation is 0.2. That is how you get the, not deviation, the distance from the center is 0.2. So these are some practical examples. Let's say I made up some numbers. So Honolulu's temperature is 74, 76, 82, and 80 with the respective months. And average is about 78. So you guys remember how to get the averages, right? So we have, give me a second. Yeah, I purchased a board just today to give you guys a better experiences. So let's say the month, this is month, and this is a temp. So this is January, April, July, October. So let me turn on the light. This would be 74, 76, 82, and 80. So first thing you guys need to do is find the average. So how do you find the average? I'm not sure whether you can see better with the light or no. I think this one is better. So average is basically add all this number. So if you add this number, it would be what? So 74 plus 76 plus 82 plus 80. And then what? And you need to divide by. So since this is about like the samples, right? So you first add everything. 74 plus 76 plus 82 plus 80 divide by how many observations do we have? We have basically 4. So it's going to be 4 minus 1, right? So let me do the calculation. 74 plus 76 plus 82 plus 80. That is 300. 12. Oh, sorry. I made a mistake. 4. Oh, actually, we are talking about population for now, but I will discuss the sample later. Sorry for the confusion. This would be 78. I will come back to the sample thing a later part, but we are looking for population average. But I will cover this later. So you get 78. And what is your deviation compared to the mean? That is your deviation. Let's say deviation is -4, right? That is 74 minus 78. Similarly, 76 minus 78 is 2, -2. 82 minus 78 is 4, and 80 minus 72 is 2. So this is how you get the deviation, right? So I mean the similar concept, whatever thing you guys have minus just the average. So these are the deviations. So that was the first thing. And since the problem is that, so again, the purpose of getting deviation was we want to get variances, or in other words, we want to describe how the data was distributed through. So we first get the deviation, but the thing is sometimes it's negative and sometimes it's positive. So we don't want that to happen, because if we add this number, it's going to be canceled out or something. So we want to eliminate those negative signs by taking the square of it. So it's gonna be square deviation. It's gonna be 16, 4, 16, 2. So that you find the square deviation by take the square root of this. So that is a square deviation. This is mathematic notations. Xi is the 74 and X bar is 78 and take the square. So the variance is calculated from here. We have how you get the deviation in the end was you add all this number, right? Oh, sorry. You add all this number, right? And then divide by how many samples do we have? 4, right? So divide by 4. That's it. It's this is how you get the variances. So we have as many. I will come back how we get the variances in detail later part. But for now, just this it was how we get the variance. So we have as many square deviation as the observation. There are a new random variable. So variance is average of square deviation. So this is quite an important concept. So I will come average of square deviation. So that's why I told you 16 plus 4 plus 16 plus 4 divided by 4. That is actually variance. In other words, that is average of the square deviation. So population variance, you just true mean. Again, this is a population parameter for average, mu, and denoted by sigma square for variances. But in reality, we're not going to have a population data sets because sometimes if we want to know what is the average income or average education, etc., we cannot get all the information from the all cities in the US. So instead, we want to try to guess those population parameters using samples. That is called and based on sample, we can get the average and we can get the variance. Those are called the sample variances. So these are the variance formulas. This was the population, and this is a sample. So idea is like that. Okay. For example, let's pretend that these are core populations. Well, and the population related mean would be something like a mu. This is like a mu. It's Greek letter. And variance would be sigma square. That is a variance. But we cannot get whole data set. So we are using very small fraction of this, say this number, because we cannot offset whole data set. Using this, we can get same mean, but the notation would be X bar. And variance, same variance, but it's gonna be S squared instead of sigma squared. This is sigma. Again, it's Greek letter. So that was the concept. In formula wise, the formulas are a little bit different. I mean, when we want to get the mean, the population mean, we are just adding all numbers and divide by n. For example, if we have some mathematically, we can get mu. Mu is basically expected value of x, but this is also 1 over n, and sigma I equal 1 to n, and it's gonna be just xi. So that is how you get the mean. So that is summating all the numbers and divide by n. So one example would be, let's say, you have 5 friends. So they have some outcome like a GPA. Say one friends get 3.5, 3.7, 3.1, and 2.5, and 3.9, something like that. So 1, 2, 3, 4, 5. And you want to know their averages, and you just summate that. This is sigma. Again, it's sigma. It's a summation. It's a summation notation. So you are summating from I equal 1 to n. Here, how many n do we have? 1, 2, 3, 4, 5. So you are just adding that up. 3.5 plus 3.7 plus 3.1 plus 2.5 plus 3.9. And how many n do we have? 5, right? Divide by 5. This is how you get the average, population average. If you want to get the sample average is usually x bar. You want to calculate this by 1 over n minus 1 and sigma I equal 1 to the n and xi. So same thing over here, but you subtract n minus 1. I mean, divide n minus 1. Similarly, for this one, you would get 3.5 plus 3.7 plus 3.1 plus 2.5 or 3.9 over 5 minus 1. This is a key difference. So you are subtracting 1 for denominator. So that is a sample. This is a sample. This is a population. This was the population. Similarly, the variance, so I will erase that. Variance would be, so variance formula would be sigma square equal, that is a variance for population. This is population variance. To be 1 over n sigma I equal 1 to the n xi minus mu square. So that is a deviation. So don't worry about this mathematical notation. I want you guys to know the intuitions. So xi, there are observations from 1 to n, but this is a population mean. So xi minus mu was what? That was deviation, right? And you take the square of it. So now you have a square deviation, right? And then you summate everything. You are just summing everything, right? And divide by n. So that it was the average of a square deviation, as we discussed in the previous slide. That is a population variance. So don't worry about the mathematical notation. I just want you guys focus on the intuitions. And if you have a sample variance, that is similar idea, but exactly same, but you divide by n minus 1. Exactly same, xi minus, but this is x bar instead of mu because that was a population parameter. So other than this, you just divide n minus 1. That is a sample variances. So again, these were the two examples. In Microsoft Excel, you can use this one, but I will explain this more concept in the R program later. But the reason why we are using n-1 for sample is when n equal 1, we cannot calculate the variance. So 1 over 0, we cannot define, So that's why it's n-1. So variance was what? Just adding all the number, as we discussed, we get the square deviation. And this is basically the idea. This is basically the summation of, so I mean, it looks really fancy in mathematics outcome, but it's not really. But let me explain why. So in our example, the variance was what? So 16 plus 4 plus 16 plus 4 divided by how many n do we have? 4. So this one is 16 is basically it was what for example x1 was x1 minus mu and square. So x1 was January, that was 74, and mu was 78, and take the square of it, right? And that was what, 16. So which was 16 and plus what, x2 minus mu square, that was what, 76 minus 78 square. So that was 16, this was 4, and this was like x3 minus mu square, which was 82 minus 78 square, which was 16. And lastly, it's going to be plus x4 minus mu square. That is going to be 80 minus 78 square. That would be 4. So this is how you get the mathematical equation. But if you rewrite this, because there are 1, 2, 3, 4. So because I don't want to write whole thing. So instead, I'm wanna just using some equation, like say so some function, say sigma, that is indicating summation. So I denote as I. I is like something like a subscript. So I is starting from 1 to 4, and then it's gonna be xi minus mu and square. And just divide by n. Yeah. So the notation is not really confusing. So, okay. The next thing, so that was the population variance, which was 10. And sample variance was 4 minus 1, so it's a little bit different, right? So again, let's say you have this one for Phoenix. You have an average of 75, which is calculating from what? 55 plus 73 plus 95 plus 77 divided by 4, right? So what is the sample variance? Now I'm asking you to find the sample instead of population variance. In the exam, I'm gonna define which one you should find, either population or sample. If I don't mention it, if I don't say it's a sample variance, you can just think it's as a population variance, okay? In other words, if this is a sample variance, you should use n minus 1 for denominator, right? Try to calculate that. You might want to pause this and spend like 10 minutes or so. Try to do exactly same step and whether you can get some of this number. Just try to find the temperature and find the deviations, and then finally get the square deviation. And then just add everything, divide by whatever number, n minus 1 if this is a sample variance, or just divide by n if this is population, okay? So I will just leave you the answer, but make sure you guys pause this video and then spend some time on this, okay? So you first find the deviation and get the square deviation and add everything, divide by 3 instead of 4 because it's a sample variance. So boom, this is how you get that. So Honolulu variance was 13.33, but it has about 270, much higher. So this number describe you how much more is widely distributed. Of course, it's more. It has more range, and I mean, the data was much more widely distributed. So this, by looking at this two number alone, can tell you, okay, okay, the weather in Phoenix is more widely distributed. So now we're gonna talk about when you have a probability, what's gonna be happening, So let's calculate the variance from probability. So when you have a probabilities, the things would be a little bit different. For example, this X is the number of books on Amazon shopper purchases per visit. So X is 0, 1, 2, 3. So these are the probabilities. For example, probability of X equal 0 equal 33%. So that means, okay, when they come So I mean, the probability that somebody is purchasing 0 unit in their visit is 33 percentage. Probability that they are purchasing 1 is 38 percentage, etc. So how you get the variance would be as follows. Same thing, x minus mu, and the average would be number 1. So how did you get the average? That is 0 times 0.33 plus 1 times 0.38 plus 2 times 0.25 plus 3 times 0.04. So if you summate them, that would be average. So let me so average or mean or mean would be 0 times 0.33 plus 1 times 0.38 plus 2 times 0.25 plus 3 times 0.04. So that would be number 1. If we do the math and do the calculations, and then the second thing you want to do is find the deviations. So you find the deviation x minus mu, so it's going to be -1, which is 0 minus 1. It's 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 2 equal 1. We take the square to eliminate the negative sign, and these are the numbers. So previously, when we didn't have probability, what did we do? We just add over the number 1 plus 0 plus 1 plus 4 and divide by 4 if that is a population variance, and divide by n minus 1 or 4 minus 1, which is 3, if that is sample variance. But the difference is we have probability distributions. So those are whole different things. So if you have something probability involved in, then you need to multiply probability times those square terms. For example, 0.33 times number 1 and plus 0.38 times 0, 0.25 times 1, 0.04 times 4. You get all these 4 numbers and finally you add them. These are very important. I probably gonna ask the differences between when you have a probability and when you don't have, and how you get those variances in the exam. So make sure you guys know the difference. We look at the difference. Previously, again, I used to add 1 plus 0 plus 1 plus 4 divided by n, or n minus 1 in previous cases. But when we have those probability, I just multiply the probability and final outcome. This is called weighted square deviation. So probability weighted square deviations, then I just add them up. So this is how you get the variance. So make sure you guys know the difference. Okay, this is another example. You might want to pause this video and spend some time to get the variance and then come back to this video, okay? So let's say you have a 20% chance that you're gonna win 10 bucks, but 80% chance you're gonna get $0. So how do we get the variance? So please pause this video and come back. First thing we want to do is we want to find what we want to find, if we to get the variances, we want to find the what we want to find the mean. So it's a 0, 80 percentage, and then how much did I say? 10 bucks or 20 percentage. And first you got to get the mean. So what is the mean? Mean was what? Can you try to get the answer for this? So mean is what? 0 times 0.8. If you are confused how to get the mean, come back to the slide 3. Okay. Take my lecture I recorded and posted in the Blackboard. Okay. And then 10 times 0.2, which is 2. Right. So this is your average, and get the deviation. Right. Deviation. That was what? 0 minus 2. And that was what? 10 minus 2. So plus -2, and it's you get the square deviation. Square deviation. Deviation was what? It's a -2 square. That is number 4. A square. That is 64, right? And what would be the next step? So if you remember the previous step, I will get the weighted probability. So weighted square deviation. So 80%, which is 0.8 times 4. It says 3.2, and 64 times 0.2. That is what? 12.8. The next thing is 3.2 plus 12.8 equal 16. That is your variance. Again, when you have those probability, those are how you get the variances, okay? Make sure you guys study this enough. So this is how you get the variances. And okay. What if the scale increased by 10 times? For example, it used to be 0 and 10, now it's 0 and 100. So scale increased 10 times. Can you try to get, okay, please pause this video and try to get the variances. Okay, what happened to the variance? Can you tell us? So you might want to pause this video and come back. I will leave you the answer. Do the exactly same step. Variance became 1600. It used to be 16. Can you notice something? Oh, it increased 100 times when the outcome increased 10 times. You're right. So if data are multiplied by 10, the variance is multiplied by square of whatever multiplier. So these are some observations. Okay. Because the units are not consistent, because we took the square, so we take the square root to bring down this to some more the unit, something related to what we really want. So we want to eliminate those squared term by taking the square root of it. So that is called standard deviation. So standard deviation is calculated by square root of variances. For example, we got a variance of 16. If we take the square root of it, it would be 4. Okay. So these are how you can do in Excel, etc. Okay, if this is average and this is variance, this is to be standard deviation. Standard deviation is calculated by square root of this number. Some of the examples. Now consider you first paid $2 for the gamble. So you got to pay $2 to play the gamble. That means 80% chance you're losing $2. Or you win $8. So that is, it used to be 10 when you didn't have to pay $2, but it became 8 and -2 respectively. What is the standard deviation of this gamble? Please pause this video and try to go over exactly the same thing we just went over. The answer is actually exactly variance is 16. Standard deviation is still square root of 16. This is a really good observation, because adding a number or subtracting a number does not affect the dispersion. It affects average, it doesn't affect the dispersion. Graphically, this is the cases. For example, dispersion is measuring what? How the data is distributed, right? So for example, if data used to be something like that, if we are subtracting something, everything will shift left by this. But we are interested in the dispersion of data. So dispersion of data was variances or standard deviation, but this one doesn't change when we shift to the left or right. It doesn't affect error. So when you are adding or subtracting to the whole distributions, it doesn't affect your variances or standard deviation, but it affects the mean. The mean used to be some number, but now it's decreased to this number. So this is mean would change, but variance wouldn't change. So that is some observation because the center moves together and the effect is cancelled when calculating the deviation. So you can do the math, see, those are the same, you know. So standard deviation, let's say, I mean, these are some of the observation when you, for example, multiply 10 to the data, variance increase a square, for example, 100 times. This was the example from this one, for example, when you are multiplying 10 times, the variance increase 100 times. That is because mathematically it's from here. So variance of y, if this is, if we multiply a, it's going to be a square. And standard deviation, which is you took the square root of it, this is how it's changed 8 times standard deviation. For example, if your standard deviation was number 4, right? And then if I multiply the data by 5 times, then your standard deviation will be 5 times 4, which is 20. But your variance would be, you know, you need to take the square root of whatever I multiply, for example, 5. So it's going to be 5 square. So these are some examples like your SAT or GPA, you know, I mean, standard score. This is actually quite important. For example, once students have a SAT score of 1700, that is based on 2400. It's old SAT, but GPA of 3.0, how we compare them. So sometimes the comparison might be easier if we can compare with the standard deviation. For example, I mean, average SAT score is 1500 and average GPA was 2.5. That means, okay, it's a 0.5 percentage. That is our deviation, and 200 it's a deviation for SAT. But can you tell, I mean, using this absolute value, 200 and 0.5, can we compare? No, we cannot compare the two students because the units are not the same. So suppose that standard deviation was 100 and 0.2. You guys know how to get the standard deviation now, right? So we can so that means, okay, the 0.5 difference for GPA was because their standard deviation was 0.2. So if we take, if we divide 0.5 by 0.2, that would be 2.5. And those 200 divided by 100 would be 2, so this is 2. So graphically, this is how it would look like. So when you have a distribution, for example, SAT distribution, and this is your average. Let's say average was what? In our cases, I said 1500, but you are in 1700, right? So you are 200 plus, but in terms of a standard deviation, because pretend we have a standard deviation of 100. So the 200 difference would be 200. This is a deviation divided by standard deviation, which I just gave you in this example, 100. That is 2. So you can tell using this data that, okay, 1700 score is 2 standard deviation from mean. This is how you describe. So in terms of SAT, that is a 2 standard deviation from average, but GPA is 2.5 standard deviation. So student 2 beats the average by a larger margin in terms of standard deviation. So if we know some like a distribution, 2.5 is basically 2.5 is much higher, far from the mean than 2. So student 2 beats for students. This is one of the examples we can use. So use those standardized. So when you're doing standardized exam, for example, SAT, I mean, as soon as you get the SAT score, they say, okay, you're, 90 percentage percentile or, 75 or et cetera, et cetera. These are all based on this one. I will go over this in detail, very detailed later, but these are some standardized scores called Z-score. I will come back this later. These are some functions in Microsoft Excel and standard errors that which I will cover later more detail, but standard error measures the accuracy of the sample mean as an estimator for the population mean. So we will definitely go over this later, but this is how you get the formula. So standard deviation was square root of variance, but you just divide this by square root of n. N was the sample size. This is standard of error. But this is when it comes to mean average. I will go over this in detail later, but for now, just take it as granted. And mode is most frequently occurring value. So mean is measuring average, median is in the middle, and mode is capturing most frequently occurring value, which would be here. This would be your mode over here because that observed the most. So these three are most commonly used. Most of the time, maybe you will focus on mean and median, but sometimes mode is also very important. These are some examples like unimodal and bimodal and uniform multimodal. So I will go over this, a couple of things bimodal, for example, later, but for now, you just know what would be modes. You can skip this chapter. And skewness and kurtosis, you can, this one is measuring, for example, so far we were talking about very symmetric observations, but sometimes observation is something like that, and sometimes it's more like that. So this is a skewed right, and this is skewed left. So this is skewed right. So measure of this one can be done by this one. So when you want to describe those data set, for example, the data is skewed right, then you can actually measure how much skewness it has using this formula. But for this course, I think you can just know the variances and mean, but skewness I probably cover later, or I'm not sure yet. But you just keep in mind that this was how we get the variances, but just that was square. But if you take the cube of power of 3, it's gonna be skewness. If it's power of 4, it's a kurtosis. So probably cover later. So this is a negative skewed and positive skew. Sometimes people say skew to right and skew to left. So it's a skewness is measuring symmetric about the mean. If you don't have any skewness, it's gonna be just symmetric, something like okay, like that. Oops, more like this. So very symmetric, but this is basically not really symmetric. But probably I'll talk about this a little later. Okay. If you guys have any question, feel free to let me know. Okay. Thank you so much.